All right, so let us wait 2 more minutes for the others. Oops, I guess all of you are already in here. So 17 participants. So may we now continue our discussion? Hello, are you guys already there?
Yes, sir. Yes, sir.
Okay. So I hope the others who didn't answer are also already in here. All right, so maybe we'll just wait 1 more minute. Maybe some of you did go to bathroom or CR for 14. And now we are now 18. Right. So let us now continue our discussion. So we have just finished this one subset of a set. So do you guys have any question or clarification so far?
None, sir.
What?
Answer.
All right, so none. Okay. So let's now move on to the next one. So we have here Venn diagram. So we have here the it's used to show the relationship between sets. So we have here circles. So we have this Venn diagram and then this Venn diagram. So those Venn diagrams are named after British logician John Venn. So maybe he's the one who have an idea how to create such diagram wherein it's called now Venn, right? So as you can see right here, A is a subset of B. And again, this set is under the superset, or all of the elements of this set this can be found on our set B. Okay. So as you can see, it is only a small portion of our set B. Okay. So for example, set B contains 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then letter A only contains 1, 2, 3, 4, 5. So in that case, this set A is a subset of set B. All right. And the other one here is set E and then set B, wherein they have their own distinct elements, and then some part of it are common. Okay, so maybe there's 2 or 3 elements wherein they are common with each other. So that's why they've intersected with each other. So later on, we'll discuss what is intersection, union, and so on and so forth. All right. So first, let's discuss more about subset. So subset examples. So what are the subsets of set A 1, 2, 3? Okay, so here are the solutions. So all of those are the answer for this set A. Okay, so we will start with empty set. Okay, because initially there is a part wherein it's empty and then it's just filled up by element 1, element 2, and then element 3. All right, so that is why we have here an empty set as part or as a subset of this set A. And then, of course, 1 is a subset of set A, 2 is a subset of set A, 3 is a subset of set A, 1 and 2 is a subset of set A, 1 and 3 is a subset of set A, 2 and 3 is a subset of set A, and then 1, 2, 3 is a subset of set A. Or again, subset or any set is a subset of itself. All right. So as you can see, we've just put all of the possible combinations of the elements wherein we call that one subset, right? So did you guys get this one so far? How did we arrive with those solutions?
Yes, sir. Yes, sir.
Yes, sir.
All right. Good. Next, we have your subset example number 2. So let A and empty set be a set. Thus, empty set is a subset of set A, just like what we did in here as our first answer. So for number 3, if A is a subset of B, then B is a subset of A, then we could say that A is equal to B. Okay. Or A is a subset of B, or it's right in here. So that's why A is equal to B. Anyway, we have here an OR wherein A is a proper subset of B, which is denoted by A proper subset B. Okay, so when say proper subset, actually I wasn't able to put any definition of proper subset here. But when I say proper subset, okay, let's change this one. It's not OR, okay, because A is not a proper subset of B. So there's a correction in here. We can only say that it's a proper subset if it's not completely the same with our superset. Okay, so all of the elements, for example, all of the elements of set A should be able to find or should be able to found on set B, but there are some elements of set B that cannot be found on set A. So that's our minimum requirements when it comes to proper subset. Okay, so the word proper should be literally under. Okay, the superset should be literally under with our proper subset. Okay, they cannot be equal with each other. Okay, so A should not be equal with B. B should not be equal with A. Okay, our superset here should have more elements than our proper subset. All right, so there should be at least one that is cannot be found on our proper subset. Right. So I hope you were able to get this one. Anyway, this one is super easy when it comes to differentiating this one with subset. Just look for more examples on the internet. Okay, since I wasn't able to add more example for the proper subset. Okay, so next one here is the power set. Okay, so let me just make this one much more understandable. So when you say power set, you're trying to put or indicate all of the possible combinations of that set. Okay, so here's the first possible representation of that set. So we have empty set, we have 1, which is 1, and then we have 2, we have 3, we have 1, 2, we have 1, 3, we have 2, 3, and then 1, 2, 3. Okay, so we call that one power set, all of the possible combinations of a certain set. So for you to be able to find out what are or the counts or how many elements that you can make out of a set, so just memorize this formula. So 2 raised to n. Okay, so what is that n? N is the count of elements of that certain set. So in here we have 3 elements. Okay, 1, 2, 3. So that is why 2 raised to 3. So just solve this one. So 2 raised to 3 is equal to E. So if there is an empty set, okay, so 2 raised to 0 is equal to 1 because any number that is raised to 0 is 1. So an empty set has one possible combination, which is an empty set. Okay, and then 2 raised to 1, so having one element. So the first combination that you can indicate here is, of course, the empty set and then the one element. Okay, and so on and so forth. Okay, so in here we have 3 elements, so it's 2 raised 3, which is equal to 8. Okay, so in here, as you can see, we have here the called cardinality. Okay, so this one meaning there's 8 possible combinations that you can make out of this set or the power set. Okay, or in other terms, you call that one cardinality. So did you guys get this one so far? Power set.
Yes, sir.
Yes, sir.
All right. So again, if there is, if you have a question or clarification, then feel free to ask me anytime. All right. So next here is the example of power set. So what is the power set of the empty set? Okay. So as I said a while ago, an empty set has one power set or one cardinality, which is the MP. Okay, or empty set or null set. And then what is the power set of the set? So this one is a set wherein it contains another element, which is a null set. Okay, so this one has 2 elements. Okay, the first one is, of course, the empty set, and then the second one here is the literal element, which is the null set. Okay, so we have 2 cardinalities for this one. So right after that, you're going to have a sleep break again. Okay, so yeah, true or false, just identify whether this one is true or false. So natural number is a proper subset of R. Is it true or false? And so on and so forth. Okay, so just answer this one in Canvas. Okay, so I have already created a new module for this one and then the following activities for this one. So just check that one on our Canvas. right? So any concerns so far regarding with the seat break?
None, sir.
All right. Okay, next. So we have here finite set. So if you already know what is the meaning of finite, then you already have an idea what is a finite set. So finite is a countable, okay, or it any set that can be listed. As long as you can list it one by one, then that one is called a finite set. Okay. But if you cannot list it, like for example, it's now infinity, then that one is already under infinite set. Okay. So finite set is elements of the set that can be listed. Okay. Or the cardinality of a set A is denoted by this one. Okay. Set A, wherein this one is the cardinality. Okay. So if you can see this vertical line, and then it has a set inside of it, we call that one cardinality of set A. Okay. Meaning you're counting for the possible combinations of that set. Okay. So as you can see right here, we have one, I'm sorry, numbers only, the counts of elements. Okay. Not possible combination because that one is for the power. Okay. If it's something like this, it's just simply the count of elements. Right. So that is why in here we have 1, 2, 4, 5, 6. So this one has a cardinality of 5. Okay. It has a count of 5 elements inside of that set A. Right. So that's it for finite set. And then cardinality examples. So we have here 1, -13, 4, -13, and then 1. So can you guys guess how many elements or what is the cardinality of set A? Anyone who can answer number 1? What is the cardinality of set A?
32, sir.
30? No, no, no. That one is for the power set. So power set of set A. So again, I'm sorry for that one. I might have caused confusion from what I have discussed a while ago. So cardinality is just the count of elements inside of it. So in here, we have 5 elements. Okay, so that is the cardinality of set A. 1, 2, 3, 4, 5. How about number 1?
5, sir.
5? Wrong. Any other answer?
3.
So there's
3, sir.
only 3, okay? So you have to take note that you have to remove the redundant or the repeated elements. Okay, so in here, there is one repeated -13 and then one repeated +1. So you have to remove the other two and then just retain the distinct elements, which is 4, -13, and then 1. So in here, the cardinality of set A is 1 only. Sorry, 3. How about letter B? What is the cardinality of set B? Anyone? Cardinality of set B. So there's only 3. Yeah, that's right. So this number 3 and then this element here. So again, if there is a set inside a set, we don't care how many elements or what are the elements inside of that set. This one is just one element. And then the last one is a null element. Okay. So 1, 2, and 3. How about number 3? What is the cardinality of set C?
1.
Okay, so that's different with power set. So if it's power set, then this one has one element. But since what we are asking here is the cardinality, we cannot count anything, then this one has a 0 cardinality. Okay, so this one is 0. How about number 4?
0.
Number 4, 2. So in here, there's now 3. Okay. So we have here the first one, okay, which is, so take note, this is our first set, okay. And then anything that is inside of it, so it could be a set or it could be just a simple element. So it is already counted as one as long as it's separated by comma, okay. As you can see right here, this one is separated by comma, so this one is one set already. Sorry, one element, okay, another element, and then another element. So number 4 has 3 elements. But in here, it's just a set, but it contains nothing. So that's why number 3 is 0. But for number 4, we have 3 elements or 3 cardinality of set. Right? So I hope that you guys were able to fully understand what is cardinality. So that's the difference between cardinality and then power set. Okay. All right, so next we have here infinite sets. So just like what I've said a while ago, so infinite cannot be listed. It's like z plus because it's infinite, positive integers. We also have z, which is negative integers, and then positive integers, wherein it's infinite also. So that's why it's under infinite set. We have natural numbers, which is also infinite, rational numbers, which is also infinite, and then real numbers, which is also infinite. Okay. So once you're done with those topics, then you may now proceed in answering this next secret of yours. So this one's super simple. So for the first one, here's instruction. So write the set in the form x such that proposition x or p of x. Okay. So you have to form an expression or what we call this one, annotation. Okay. Having these elements. Okay. So what are the example of those? Power sets. This one. Oops, not this one. This one. Okay. So you should create something like this, wherein it should only contain 2, 4, 6, 8, 10. Right? The same with number 2. So this is actually like a bonus already. Okay. But in annotation form. Okay. IEO. And then 1, 8, 7, 6, 4, 1, 2, 5, negative 2, negative 1, 0, 1, 2. Okay. And then the next one here is if A is equal to 3, 7, 12, find the cardinality of A, power set of A, and then the cardinality of power set of A. Right? So in here, so for the first sit work, let's just go back on that one. All right, for this sit work, listing the elements. So this is your second sit work. Yes, that second sit work. So do this one on the Microsoft Word, just like the first activities that we already did. So using Microsoft Word, so answer this one and then upload that in our Canvas. So the same with this sit break, yeah. So answer this one using Microsoft Word 1 to 4. The same with 5 to 7, and then submit this in our Canvas. Okay. And the same with this one. So this is a continuation. So 1 to 7, and then 8 to 13, and then I guess there's more. Yeah, 14 to 16. So all of those for this sit break, writing set into a form. So 1 to 17, do those numbers 1 to 17 into Microsoft Word and then submit it as of course a Microsoft Word format. All right. So here's the next sit break. So using the Venn diagram, identify the following as true or false. So this one is super easy. So 8 to 13 is just true or false. So just write here true or false. So simple as it is. And then for number 14 to 16, so it's now the opposite. You are now the ones going to create a Venn diagram for these conditions. Okay. So do you guys have a question or clarification so far?
None, sir.
So here's the first one, 1 to 7. Here's the second one, true or false. And then here's the third one, 14 to 16, drawing or creating a Venn diagram. Any concern or clarification?
None, sir, none.
Okay, so if ever that
Wala po.
okay, that's good. So if ever that the instruction is not clear or you cannot understand what are the things that you need to do, so feel free to ask me on my Canvas account or to my Facebook account. Okay. All right. So next one here is operations on sets. So under operations on sets, we'll discuss union, disjoint union, intersection, set difference, complement, symmetric difference, and then partition product. So for some of these, we have already discussed some in our Part 100. So maybe you already have an idea what are those. So first one here is union. Okay. So when we say union, it's a set of consisting of all elements that belong to A or set A or set B. So you can denote this by A and then U or union B is equal to X is an element of A or X is an element of B. So for you to be able to understand this one a little bit more, so we have here the Venn diagram wherein A union B. So we have here the distinct elements for set A and set B and then their common elements. Okay, so we have here the example. So set A contains an element of A, B, C, E, F. And then set B contains an element of B, D, R, S. So all you need to do when we say union, so just combine them. Okay? Just add or just simply combine them. Okay, all of the elements of set A and then all of the elements of set B. Okay, so A, B, C, E, F, and then B, D, R, S. And then the next thing that you need to do, since this one is a set, okay, so you have to remove the redundant elements. So in here we have a repeated element, which is letter B. So letter B only. So you only have to have one letter B only. So you have to remove the other B for this A union B. Right? So did you guys get this one?
Yes, sir.
Okay, super simple, right? So just combine the two set and then just remove the repeated elements. Right, so let's move on to the intersection. So from the word intersection, so it is the element wherein they intersected with each other. So it's a set of consisting of elements that belong to both A and B. Okay, so if you're going to answer this one, this union example, so their intersection part is letter B only. Okay, because that's the common elements. So that's the part where they have intersected with each other, which is letter B, right? So in here, it is in the form of X is an element of A and X is an element of B. So we have here a Venn diagram, and then for you to be able to appreciate this one, so we have here an example. So A is equal to A, B, C, E, F, and then B is B, E, F, R, S, and then C is A, P, U, V. So find A intersection B. So what are the common elements of A intersection B? So A intersection. So what are those elements? So where did they intersect with each other? Hello? Are you guys still there? So B, E, and F. So coming from Mr. Rava. So let's see, B, E, F. B, E, F. Okay. So yes, he is correct. So B, E, F. Okay. How about letter B, A intersection C? So coming from Miss Maxine, very good. So letter A only. Okay. How about letter C? So B intersection C. below. So where did they intersect with each other? So wala po coming from Miss Chelsea. So yeah, that's right. So if that's the case, then just put here empty set. Okay, since there is no element that they have intersected. All right, so did you guys get this one so far, intersection?
Yes, sir.
Yes, sir.
Very good. So if we have union intersection, so we also have disjoint sets. So just like what we have in here, or what, the last example, B intersection C, that one is already called disjoint sets. So sorry for that one. I have my dog in here. So as you can see, letter A has its own distinct elements, and the letter B has its own distinct elements, wherein they have no common elements. Okay, so that is why we call it disjoint. They are not connected with each other. Okay, and then here's the proper symbol for disjoint union. Okay, so if A and B are disjoint, so disjoint union operation is well defined, meaning letter A is well defined, letter B is also well defined, wherein they, just like what I have said in here, they don't have the same elements, okay, or they don't have common elements. And then for the symbol for the disjoint union is a union wherein it has a circle, okay, above this union symbol, right? So next one, here's a continuation for disjoint union. So in a disjoint union of finite sets, cardinality of union is the sum of the cardinalities. So you can only do this one if this one is completely a disjoint union. So if they are disjoint, they have their own distinct elements. So you can just simply add their cardinalities. So cardinalities for set A, and then cardinalities for set B. Okay, so just add them for you to get the total elements of those two sets. Right? So we also have here difference. So difference here is a set of all elements that belong to A, but not in B. So it is denoted by A minus B. So X is an element of A, and X is not an element of B. So here's the Venn diagram for the difference. So yeah, it's quite confusing. But any elements that is in A, you have to remove that one also. That is why this B is subtracted with our set A, including their common elements. All right. So we have here more examples for the difference. So we have here set A, wherein contains A, B, C, and then set B, B, C, D, E. Okay. So if we have A minus B, okay, so take note A minus B. So here's the set A, and then here's the set B. So the first thing that you need to do here is remove all of your common elements, which is B and C, okay? And then just never mind the other elements that is not the same with this set. So B and C only, so deduct this B and C with our set A. Okay, so that is why A minus B is equal to A only, okay? So this is their common elements, which is B and C. So just remove that one also. So just retain the element of set A. And then if we have B minus A, okay, so you have to remove all of their common elements, which is B and C again. So just retain all of the distinct elements of set A, which is D and E. Okay. So for the difference, so you have to be aware to their arrangement. So whatever is on the right side should be the one that is will be subtracted or reduced or removed or eliminated with our left side set, right? And then here's the Venn diagram for the B minus A. So were you guys able to follow this one?
Yes, sir.
Yes, sir.
Are you guys confused? Not really. Or maybe. So if you're
Konting
confused,
practice, sir.
Konting practice. So if you're confused, so just go back in here again and then just try to analyze it one by one. All right, so that's it for the difference. So we also have here symmetric difference. Okay, wherein in symmetric difference, set of elements that belong A or B, but not both A and B. So basically, in symmetric difference, you just have to eliminate your common elements. Okay, so here's a symbol for symmetric difference: A, X, or B. Okay, wherein X is an element of A, X or X is an element of B. Okay, so we have more example for each one. So we have here set A, B, C, D, and then set B is A, C, E, F, G. Okay, so what are their common elements? So we have here letter C and letter A. Okay, so just remove those elements and then just retain their distinct, unique elements. Distinct na unique pa. All right, so anyway, so we have here B, D, E, F, and G. So we have removed their common elements for symmetric difference. Did you guys get this one?
Yes, sir.
Right, so in here, arrangement doesn't matter. So it could be BX or AX or B. Doesn't matter. So we have here also complement, okay? Or in loss of logic, well, we call this one negation, okay? So universal set U, A, is denoted by this one, okay? So X is not an element of A, okay? If ever we have this A complement, okay? So basically, if we have this set A, and then if you're going to negate this one, so of course, just get everything aside from this set A, or the opposite of the set A, which is the complement A. Okay, so as you can see, we have here a boundary wherein we call this one universal set. So from the word itself, universal, it's like the universe. Okay, so imagine this one as the earth, and then if you're going to complement the earth, so anything aside from earth, okay, which is this entire shaded yellow, right? So did you guys get this one or no? Yes or no? Or 50-50?
50-50, sir.
50-50. All right. So since I don't have example for this complement, so I highly suggest you guys to search for more examples when it comes to complement. So in here, I just simply let you know what is the concept behind complement. So anyway, that's it for the complement. So we will discuss this one soon if ever you guys didn't really get this one. But this one's super simple, so that is why I didn't include an example. Shh. Anyway, so we have here set identities wherein super similar with our loss of logic. Okay, we have here commutative, associative, distributed, idempotent, properties of the complement, properties of universal set. So this one is quite new. And then properties of the anti-sets. This is also new. Okay, and then properties of absorption. So this one is also on the loss of logic. Okay, so I will not discuss those properties anymore since you guys have already know this one. Okay, just by learning the loss of logic. Okay, so it's 1 to 21, right? Or is there anyone who wasn't able to understand the loss of logic? All right, so I guess none, because if there is, I'll just scold you, okay? Meaning you didn't really study at all. Okay? So those are the fundamentals of our module 1. Okay, so I'll leave this one as your self-study rules or properties. Okay, so we have here proving example. So we have to prove that this left side expression is equal with this right side expression. So it says here, not only prove, but you should use a Venn diagram. Okay, so take a look on this one first. This is the left side expression, which is this one, A union B. So this is like the same with the De Morgan's law, okay? But in a form of complement. This one is a big complement or big negation, okay? So the first thing that you need to do here is, of course, draw the Venn diagram of set A, and then the Venn diagram of set B. And then A union B.
Church ko lang, uncle. Church ko lang man.
S.
Ay, laptop ay.
So pakimute na lang yung mic pag hindi ginagamit para hindi nakaka-distract. Anyway, so we have here the Venn diagram of A union B, okay, wherein we are now combined with each other, and then just complement this one, okay? So you can get anything aside from this A union B, which is now this universal set. Okay. So we have to prove that this Venn diagram is equal with the other side expression. So same, you have to indicate here what is not A. So this is our A. If you're going to complement it, then just get everything aside from set A. So the same with set B. Get everything aside from set B since it's complemented. And then just simply combine them using A intersection B. Okay, so A intersection B is now this Venn diagram. So in this case, this right side Venn diagram is now equal with this left side expression, or left side Venn diagram, sorry. All right. So since we don't have enough time anymore, so we'll just continue the rest on the part 3. Okay. So if you have questions regarding with this one, then we will continue to one on part 3. So for now, goodbye, and then see you on